Hello and welcome everybody. Welcome back to this video. Today I'm going to focus on two things. Well, one that is going to be around two subtopics in a way. We're going to talk about network topologies. Okay, we're going to focus on the bus topology and on the star topology. If you want to follow along this video, I'm going to link here if I remember to do so, which was about MAC addresses. You should see that one first, but however, this one you can also see the one as it is. And we're going to discuss about star and bus topologies. Stay with me and let's learn together. Okay, if you have the time and availability, please like and subscribe. It really helps the channel out. If you have the time and the patience to do so. And if you enjoy these videos, please do. It really helps the channel and keeps me keeping forward and growing this channel. Okay, so this topic today is going to be about the bus topology and about the star topology. This is somewhat a follow-up of that first video about MAC addresses, where I said that MAC addresses were used especially on the local network. Okay, so MAC addresses are not spread out throughout networks. They do not go after, do not traverse routers. You actually should see that one first. So this one can fit into that, but this will also stand okay as it is. So let's discuss about topologies. We're going to just discuss here two main topologies. We're going to discuss star topology and the bus topology. Actually, on the other way around. First, we're going to focus on the bus topology. Then we're going to focus on the star topology. And I am brave enough to say that these are the most common topologies these days. Some of you guys might be kind of tweeting on the chair saying, but I actually know other topologies. Yes, there are other topologies different from the bus or the star, but the bus and the star are the ones that actually are the ones that actually matter because they are the most used ones. And if you are preparing yourself to some sort of certification, like the CCNA certification, those are the ones that actually matter to understand, so you can actually pass those certifications with success. Now, I'm going to focus on my tablet here, so I'm going to look down for a bit. I'm sorry for that, but there's where the tablet is. So let's focus on these pictures now for the following minutes. So I said in the previous video, if you saw it, let me just quickly summarize that MAC addresses are physical addresses that are born in on the network cards of our devices that allow them to communicate on their local network. So they are different from IP addresses because they operate on a different layer. I will also make a video about the OSI layer, the OSI layer, OSI, OC. There are many ways to say that. Stay tuned, like and subscribe so you can check that video out also. I will focus on that on a specific video. But on this one, I'm going to focus on topologies. And what are topologies, you may ask? That's kind of a good point to go through. So topologies are ways to connect our networks physically. Okay, so when we build our networks, when you actually start building with cables and devices, etc., we based ourselves on topologies. Okay, and topologies are ways to connect devices to one another. That's as simple as that. So when we went, and let's focus on the LAN for now, local area networks, our local networks here, enterprise, corporate, etc. We need to decide which topology to use. And there is one that we use nowadays, or a deviation or adaptation of that. But that is based on older. And by older, I don't mean less good. It's just older. We usually base our networks on a specific technology topology that I like to consider it to be the kind of the mother or the father of most LAN topologies today. So if you understand that topology, you will be quite comfortable to understanding others that are mostly based on that one. And that topology that I'm mentioning is the bus topology. Okay, so let me pick my pen here. Yes. And we're going to analyze for a few minutes the bus topology to start. Okay, so the bus topology works as follows. So I'm going to make a schematic here of how the bus topology works, and then I'll do a more in-depth analysis of it. So basically, the bus topology, it's a topology that we connect our devices literally like this. So if you see the little balls here as computers, printers, telephones, whatever, this is our bus topology. So everything is connected to one another with a single conduction point. So if you imagine this like a clothesline where you just put your clothes to hang and to dry out, it's not that different. So we have a common connection point, which is that this dash here, this line here. This is our common connection point to all devices. Okay. Now, this is an actual reality in a few days ago, not days, years ago, that are going to represent here the devices that we use physically to construct or to build a search topology or search network. So let's imagine that I'm doing a bird's eye view of a computer. So I'm looking down to the computer, and this is the back of the computer. Okay. Usually the back of the computer will have something sticking out where we would connect a thing that we call the T connector. You see, this was a literal T, and you can Google this. Just search for BNC T connector. Okay, and you'll see what I mean. It was literally a T plug that would allow the cable to connect to one side and leave through the other. Okay, and also it had one of the connections would connect to the computer itself. So this was and is the T connector. So it will connect on a network card on the back of the PC. The cable will come in here and continue on to the next PC. So if I do a schematic where I can put two PCs, this is a bird's eye view, the top down. I'll put 3. That's fine. So the network card will have something sticking out, a plug sticking out. We would connect the T plug here, the T plug here, the T plug here. The cable would just traverse all PCs like this. Okay. So basically it would result something like this, where the cable would just enter the quote unquote first PC. It will then go to the second PC, third PC, and so on and so forth. Okay. We would use coax cables. Okay. And also the plugs here or like BNC connectors. We still can find BNC connectors everywhere, like monitors, audio devices. So the BNC connector itself, it still survives. It's still used today and very effectively, actually. And the coax cable is also used on some other situations nowadays. But I will just put this into perspective as an older technology. But it's the idea here, the cables and the connectors may be used, or are still used in some situations. Okay. But they are very niche and specific situations. So let's assume that this is kind of the starting point of the modern LAN technologies. All right. So this is basically the bus. And also in the end of this, we had to put one thing that we call the terminator. Okay. This would literally a BNC terminator. Okay. This would literally terminate our network. So the left-hand terminator will mark the beginning of the network, and the right-hand terminator will mark the end of our bus network. If this connector was to be disconnected, or if it failed, the network would completely stop working. Okay, or if the terminators were okay and the network was cut by something abnormal, someone will trip on the cable would fail, someone will just make the chair over the cable and will break the cable, because coax cables have a solid core made of copper, so it's easily breakable. If some abnormality would occur on any point of the network, it will make the network completely stop. Okay. So it worked while it worked, but it was very prone to problems. Like the terminator can fail, and then everything would stop. If I break the cable at some point, the whole network would stop. So there were many possible causes to problems. The coax cables also could be considered thin or thick. Okay, so we had 2 versions. We have the thin version and the thick version of the cable. So the thin version It's like if you are in Europe, you know what I mean by this. It's very similar to coax cables used to TV signal antennas, and the thick was really, really, really thick. It was very hard to bend. It was not supposed to bend, but if you had to do some bending, it had very little leeway to bend. The thin had more leeway, but it was more flimsy and more prone to problems. So usually the thick cable, we use it to like the backbone on our building from top to bottom, and the thin cables would be used to actually build the networks along the where the PCs were and where the PCs that did the network were located. Okay, so thick, it was the backbone, and the thin was the local network. But in the end, everything ended up in a schematic like this. Okay, just bear in mind that we had 10 megabit, okay, 10 megabit performance in a good day. Okay, so in a good day we had 10 megabit performance. What I mean by a good day is that this would be the top performance that we could get with such network type. Okay, because since one of the things that it's a characteristic of the bus network is that the network is shared. Okay, so everybody that was plugged into those thick and thin cables, we were sharing the network throughout those devices. So let's say I had 100 PCs, so the whole network was sharing. The whole 100 PCs were sharing and competing for that network. So those 10 megabits were not actually 10. We could do a simple basic math just to be representative. You could divide 10 through all the active PCs. This is not very accurate, of course, but it can give you an idea that there was a competitive way of transmitting data. Everybody was competing for that thick net, thin net, that bus. So, for example, here we have 1, 2, 3, 4, 5, 6, 7 PCs just randomly drawn. So basically, our bus all the 7 PCs are competing for that bus. So the more PCs you would put on that bus, on those thick and thin cables, the more competitive it was, and the more sharing of resources that would occur. Okay, of course, nowadays, if you are starting to study this, you probably already heard about 1 gigabit, 10 gigabit, 80 gigabit, 100 gigabit networks, which is getting more and more common these days. 10 megabit looks a little bit kind of a joke, but 10 megabit 20 years ago, around about that, it was considered a very high-end network, so you guys can see. Okay, so let's focus on the bus network with 4 computers, just to make things simpler to analyze. So we have here the terminator, all the T connectors connecting the PCs, and we have 1, 2, 3, 4 computers. You can represent 440, 400, whatever the case. If you had a big building with thick net and thin net cables all over the place, it was a big challenge to give quality network to everyone. And if the network would fail by some reason, it was a big challenge to find out where the problem was, because any break on the copper throughout the network could be the cause. And it was a big challenge to find out where the break was and to fix it. It was very challenging and sometimes time consuming. Yes, there were tools, actual physical tools that would help us to try to troubleshoot that, but they were very expensive at the time, and it was literally time consuming. I spent many, many hours on my knees and crawling under PCs, finding out possible failures for the cables, possible failed T connectors, possible failed terminators, etc. I had a bag with goodies like nowadays, but those goodies at those days were terminators, T connectors, coax cables, just trying to find out where the problem was and try to fix that issue. Okay, so we have 4 PCs on the bus network. We have T connectors and we have the terminators at the end of this network. So how was data transmitted? Well, it was quite simple. uh, at this point in time, MAC addresses were already a reality. So let's say this is MAC address A, MAC address B, C, and D. So let's say MAC address A wants to send data to MAC address D. So it was quite. I will also make a video about how Ethernet frame works. So if you wish, you can like and subscribe to get notified when that video comes out, and you'll get notified about that, because I will make a video about Ethernet frames too, and then you can learn about that at that point. Okay, but let's just say that PCA would build Ethernet frame directed to PCD. Okay, he would put this on the cable. And the thing is, when this frame gets to the cable, this frame will get dispersed to everyone. This is what he called a shared network type. So this cable is shared by everyone. Okay, so everyone is sharing this cable. So when PCA puts the Ethernet frame to PCD, even though the frame, like and subscribe to learn about that later, but even though the frame would be clearly specifying that the destination is PCD with its MAC address, since this is a shared network, the cable is shared by everyone, everybody would get this. B would get this, C would get this. Even though the frame is directed, this is a shared media, okay? So even though the Ethernet frame was completely directed to PCD, since this is a shared media, everybody will get that information. But B and C know that frame is directed to D and will ignore it. Let's not discuss exceptions. Let's just accept the truth as something absolute, even though it could not be the truth. It may not be, but let's believe that for now. So A will send the frame to D, but since this is a shared network or shared physical connection, B and C will also get that frame, but they will be careful to discard it because it's not for them. So let it go. It's not for me. I will ignore this because the destination is D. Eventually, this will get to D, and this is how it works. So everybody will build its frames, put the MAC addresses on the destination address of that frame, and he would put it on the cable, and hopefully it will get there. That was kind of the mindset. Hopefully it will get there, and many times it would. That's fine and dandy and fun and cool, but let's talk about something that could happen. Let's put this in different colors. Yes. I don't want to learn more. So machine A will put the frame to machine D, okay? And don't show this again. And machine B will send to machine C. So as you can see, there is a cross information here. So A wants to talk to D and B wants to talk to C. What happened here? And in this specific point in time, something occurred. That is, on the shared cable, two frames were sent at the exact same time. And you may be thinking, can this happen? Yes, it can and it will. Because the more PCs are on this shared network, don't forget you have these thin net, thick net, etc. The more PCs that are sharing this network, the possibility of this, what they call a collision, it's increased. So if you have two PCs, it's small, 4 PCs, it's more, etc., etc. When you have hundreds of PCs sharing the same shared network, this collision may occur, or maybe it is guaranteed to occur. Okay, this will occur for sure. So when the collision occurs, the PCs will detect this. And again, you don't have to program this, you don't have to plan for this. This is just something that the network cards and the operating systems know how to deal with. So the collision was detected, and by colliding, this is basically network and electrical things happening. So when two electrical things collide, they just disappear, they just explode. They are not valid anymore. So the PCs will detect this failure, the PCs will detect this problem, and then they will trigger a mechanism called CSMA. This means carrier sends multiple access. So carrier sense means that they are sensing the carrier being the cable. Multiple access is that multiple people are accessing the same shared media, the same cable. Then they would use one or the other, the CD or CA sub-mechanism. CD means collision detection, CA means collision avoidance. Nowadays on Ethernet networks, we use mainly CD. On Wi-Fi, we use CA. Again, there may be exceptions, of course, but let's just stick with something that we know. So CD means collision detection, CA means collision avoidance. So what is collision detection? It's just how I described. The PCs will detect a collision. They will detect the collision occurred, and they will trigger a mechanism called backoff, which is, okay, let's make believe you are PCA. And PCA says this: okay, I have detected a collision. Everybody will detect this because this is a shared media, right? So everybody will detect that the collision occurred, and they will trigger a backoff. A backoff is, okay, my data collided. I'm going to wait a little bit, and that's a trigger automatically started by the operating system and the network card. Let's make believe that I will wait 2 seconds. So A waits 2 seconds, B waits 4 seconds, C waits 5 seconds. So everybody will trigger a random timer to wait. So everybody hopefully will wait different times. Someone will wait more, someone will wait less, and the one who waits less will retry to transmit the frame, hopefully without collisions. So let's make believe that A waited the less. He waited less time. Okay. By waiting less time, he will start to transmit the data to the cable sooner than the others, which means that he will hopefully find a clear media to transmit. Let's imagine again that by some random chance, 2 PCs waited at the exact same time. They will collide again. And when they collide again, they will again trigger the backoff mechanism, and everybody will wait a random time. Hopefully someone will wait less than the others and will get the media clear. You try again. Hopefully the data will go through. If it collides again, they enter the backoff process again, and so on and so forth. So they will try and retry to wait the last time possible. So that's hopefully one will wait less than the others. Hopefully one will wait less than the others and get the clear path for the network. And it was kind of a trial and error procedure. And it's still true today. But it's slightly true because now we have a slightly different approach to the problem nowadays. I will discuss what a switch is. I will analyze what a switch is and how he can sort this out for us. Like and subscribe to get notified about that when I make what a switch is and how it works, and you get notified about that, and you can then learn about it. So let's focus on the bus again. So everybody will retry and retry. Hopefully he will get a clear path to the network and will be able to transmit with a clear path. The CA, it's called avoidance and not detection. Avoidance means that before transmitting, let's say, for example, let's make believe that A is going to transmit. Before transmitting, computer A will send a beacon to the network saying, I'm going to transmit. This is my turn now, I'm going to transmit. And it's going to hopefully send a message saying to everybody to shut up, and he will find a clear path through the network. Hopefully, again, okay? But CA it's not used by default. Nowadays, everybody uses CD, which is collision detection. So the more collisions that there are, the more frames collide with one another, more time is spent waiting for a clear path. So I collide, I wait, I retry. I collide, I wait, I retry. I collide, I wait. Finally, I can get my frame through. And everybody's just detecting collisions and backing off. As you might imagine, the bigger the network, the more collisions will occur, the more waiting time it will also occur. Okay? So basically, this is the bus network. It's a shared media for everyone. It uses those coaxial cables, and those thick coaxials thin coaxials, thick coaxials, the T connections, the terminators. It was a very flimsy network, very physically unreliable, but it was, let's call it cheap. It was not cheap, but at the time it was affordable to build, and it worked if you were aware of these limitations. Okay, so pull the video back and rehear all of this again, and put on the comments below if you have any questions about this topic. Now let's discuss the last thing about of this video, which is the topology that we use nowadays physically. Okay, and that topology is the star topology. How does the star topology work? Well, nowadays you have a central location, okay, and we have the PCs connected like this. That's why we call it the star. Okay, big differences here. So first, the network cards and the center of our star do not use coaxial cables. They use RJ45s. I'm sorry, 45s. Okay, which means that we are going to use a different type of cable to connect our devices. This cable is much more reliable than the coaxial cables. They use much more reliable plugs at the end. Again, like and subscribe to get notified. I will discuss those cables on a later video, and get subscribed to get notified about that, and we learn together about that topic. All right? Okay, cool. Now, when we discuss the star, this is a J, okay? We use RJ45 cables and not coaxial cables. Those cables are much more reliable, can traverse, let's say, yeah, bigger distances, and much more are easier to work with. Okay, that's all. That was a big step forward when we adopt star topologies. Another good thing. Let's believe it's a good thing for now. It's that we are not on a clothesline. We are not just using a clothesline to put computers to dry. Everybody's connected to a central location, and this central location will help us to. First of all, we had a big jump in connection reliability. We also had a big jump in performance. At this time, and at this point in time, we were discussing already 100 megabits transmission rate, a much more effective way to control collisions. I will discuss that when we discuss switches and all of that, and like and subscribe to get notified. Everybody is just connected to a central location. The connections are much more reliable. Performance is much higher, and we can use something we call the hubs or the switches. Okay, again, like and subscribe. I will discuss hubs and switches in a later video. So this was a really big step forward in terms of performance, reliability, and management of our network. No more thick cables, thin cables. No, it was much more manageable and much more reliable way to work our network. Also, let me just tell you about something else, because this video is getting too long or very long, which is we also use something that you can call it an extended star, because our hubs and our switches had a limited amount of computers they could connect, right? They have a limited amount, 12, 24, 48, doesn't matter. Like and subscribe to get notified about that video. And maybe one star will not be enough. Then we just had to get a new star and expand our star to another star. Okay, this is called the extended star. Most things that I discussed here still apply. The collisions, CSMA CDs, not the CD, especially the CA, not that much. So the collisions, CSMA CA, MAC addresses, everything applies. But instead of being one single clothesline, it's an extended star, multiple stars connected to one another. And this central point will help us a lot at today to manage our networks. Okay? Some of you may be thinking that's a point of failure. You are correct. That's a point of failure, like was the cable on our close line. This is also a point of failure. The terminator would be a point of failure. The T connector would be a point of failure. Okay, but yes, we have a point of failure here, but that can be fought. I can get redundant central points of my star. I can be redundant on that approach. And also, the devices that they are the hubs and the switches, they were and are much more reliable than the single cable that can destroy with a chair. Okay? Again, I will discuss this later on later video, but rewind the video, rewatch the main points of a bus technology, because the idea, how the bus works still applies today. So those ideas are very important to put in your minds, because the collisions, how they are detected, the fight for bandwidth, everything applies today with some adaptations. And when I record a video about switches and how they work, much of these concepts about a bus topology will still apply. So like and subscribe to get notified about that, and we will learn with me what is a switch, what is a hub, and how that actually correlates with the bus, and how the bus ideas still apply today, even if I use a bus. Even if I use a hub or a switch. Okay, guys, I hope you enjoyed this. It was kind of a long one, but it could be even longer. I can talk about this for days. So rewind the video, rewatch the video if you wish. Go and check what the bus is, how it works. Check the collisions. Check how collisions are resolved. Check what I talk about, the bandwidth competition and the bandwidth sharing throughout all the devices. This still applies today in 2023, but with some adjustments when we discuss the switches. So guys, thank you very much. I see you in the next video. Like and subscribe, it really helps. And I'll see you in the next one, and enjoy. Thank you, guys.